Hi, I'm Professor Sproul. Welcome to the Chemistry Lab. I'm going to talk today about the nature of matter. It certainly matters to a chemist as it matters to everyone. Matter is comprised of, well, let's think about what matter is comprised of. Well, it's comprised of atoms, isn't it? We all know that, atoms being very small particles. They're so small we can't see them. And so how do we envision them in a chemistry lab? How do we deal with them in a chemistry lab? Well, we need to deal with them on something that we can handle. Let's think about these extremely small particles and how we would deal with them. Well, one way that chemists have found is to talk about atoms and molecules in large numbers. And this concept of numbers of particles is very central to what I want to talk about today. The concept that converts the small nanoscopic or microscopic particles of the atom to the laboratory scale that we can deal with is called the mole. The mole is a way that we convert the very small particles to a number of particles that are large enough so we can actually work with them in the laboratory. Let's look back in history. Historically, matter was something that people tried to understand but had no experimental work that they could use to explain what this stuff was that was all around. Back in the golden age of Greece, between about 400 and 300 BC, various individuals developed concepts of what matter was. One individual, Democritus, considered nature of matter to be particulate. And as particulate matter, he considered only a certain number of particles made up all of matter. On the other hand, Aristotle, a little later, considered matter to be divisible into many parts. Well, that means that we can keep subdividing matter ad infinitum. Let me show you what I mean. Here we have what the Greeks would consider a piece of matter. It's a mission fig. And what Aristotle said was that you could take something like a fig and cut it into pieces. There's a fig cut in half, and it still looks like a fig. We could cut it in quarters. It would still look like a fig. Cut it in eighths, it would still be a fig. 16th, 32nd, 64th. Yes, it's still a fig. And so Aristotle's concept was not out of line for the ability of mankind to understand how nature was made up. But after 2,000 years, finally, people, scientists, alchemists, philosophers, had enough information that they started to question Aristotle's concept. John Dalton, a British teacher and chemist, recognized that there were ways of approaching nature where he could show whether or not nature was particulate or continuous. And what he did was he took some elements and combined them together. And he found that there's only a couple of ways that different elements can be combined together in natural state, producing a new substance. And so John Dalton really was the father of chemistry because of his realization that matter was particulate. Now, in order to understand how we can approach matter in a chemistry lab, let's consider the size of the atom. The atom is extremely small, unbelievably small. For example, about 10 to the 13th atoms, that's 10 million atoms, could fit on the head of a pin. Oh, I said pin, didn't I? Pin, yeah, here. Can you see this pin? Or are you not able to focus? Can you see that? Huh? Well, I hope so. 10 to the 13th atoms on the head of that pin. That's a lot of atoms. Consider something biological. Consider bacterium. Bacteria are those critters that you have to use a microscope to see, and you have to use a very strong microscope to be able to see. They're about a micron across. A micron is a millionth of a meter. I can't even show you how small those are. And if you took a bacterium and counted all the atoms in them, it would be on the order of 10 to the 12th atoms. That is a million atoms. Let's consider something we can actually see. I have grains of sand here. Living in the islands of Beaufort, it's nice to see these things up close. And you see each grain of sand is visible, but very small. And they contain on the order of 10 to the 16th or 10 to the 17th atoms within them. And so atoms are unbelievably small, and it's essentially impossible to count individual atoms. And yet, in chemistry, what we find is that atoms combine together in small whole number ratios. And so, in essence, chemistry requires our counting of atoms. Now, how do we go about doing this? Well, let me demonstrate with how about with figs? But let me demonstrate with various kinds of fruits. If you'll bear with me, I need to get my fruits. Well, here we have the rest of the fruits that I have. I notice I cleverly bought only Sun-Maid. Must be a good reason for that. I don't know what it is. But they had the right colors, and that's what I want, red, white, and blue. Because a teacher wanted her students to recognize the importance of our country's flag. And so what I did was I made a sample necklace, as you can see here, made of red cranberries, white or almost white raisins, and relatively blue, mission figs. And so we have a red, white, and blue necklace. It consists of 9 cranberries, 2 figs, and if you count them, 36 raisins. And so if a teacher wanted to make a necklace and have each of her students, let's say 22 students, make necklaces like this, she'd have to count out how many raisins, figs, and cranberries she'd need for the students, plus those that the students would be eating. And so how would she do that? Well, she would have to maybe take a box of raisins and count out, let's say, 100 raisins and weigh them, because raisins, like other fruits of this size, come by weight, not by numbers. No one's going to count the number of raisins in a box, but you can do that effectively by weighing 100 raisins, is finding how much they weigh, and then converting that to how much the weight of the box is. And so essentially by weighing, you can count. Chemists use the same technique. And so if there are 2 figs here or 9 cranberries, we could make a determination how much weight of cranberries or figs or raisins are needed to make 22 necklaces. The same story, as I say, is true in the chemistry lab. In order to convert, for example, raisins or figs or cranberries to numbers, we use count per ounce, because these boxes and bags are measured in ounces. We do the same thing in chemistry, in different units, of course, because individual atoms weigh what we call by atomic mass units. The atomic mass unit is the mass of an average atom, say of hydrogen or carbon or sulfur. For example, let's consider the element hydrogen. Hydrogen has 2 numbers associated with it. That number 1 we'll worry about later on. But the number above that hydrogen in this particular periodic table says that the mass of an average hydrogen atom is 1.0078 atomic mass units. Now, atomic mass unit is a unit that is very small and related to the particles in that atom. You notice that carbon over here has an atomic mass unit of about 12.0 grams, atomic mass units, sulfur about 32 atomic mass units, and iron 55.8 atomic mass units. Did you get all that? I hope you did. Iron does not have close to a whole number value, and that's because these are masses of average atoms. For example, iron doesn't consist of just atoms that weigh 55.0 atomic mass units, but also some that weigh a little more than that. And that's why we find the average weight is 55.8 atomic mass units. Well, an atomic mass unit is so extremely small, just as the atom is extremely small, that we can't deal with these masses in the laboratory. And so chemists have come up with a way of doing that with larger amounts of matter we call the mole. The mole contains about 6 times 10 to the 23rd atoms. And so to make the conversion between the atomic scale in atomic mass units and the laboratory scale in grams, we find that it takes, again, 6 times 10 to the 23rd particles to make up what is called a mole. A mole contains enough atoms to comprise a volume about the size of a golf ball. A golf ball size is about the size of a mole of iron. And I've weighed out a mole of iron, 55.847 grams actually. Iron has a symbol Fe, and that is exactly, or to 4 decimal places, past the decimal point, 4 places, 1.0000 moles. 1 mole, about the size of a golf ball. A mole of sulfur, again, about the size of a golf ball, but notice, instead of 55 grams, 32 grams. Why? Because each sulfur atom is lighter in weight than each iron atom. And so it only takes 32 grams of sulfur to make a mole. Well, we use this method of counting atoms by weighing. And weighing atoms is the convenient way of counting. So we will need to know the masses of atoms. And we do this by using, again, the periodic table, which embeds in it all of the masses of the individual atoms. Now these are elements. There are about 100 elements in the periodic table, and only 100 elements. But there are a whole lot more compounds where compounds are made up of 2 or more different elements. For example, with iron and sulfur, we can make up 2 different kinds of compounds. There is something called triolite in the mineral world. Triolite contains 1 atom of sulfur or of iron and 1 atom of sulfur. The formula then would be FeS. Would you like me to write that down? FeS. And notice that's a compound because it contains 2 different elements, 1 iron atom and 1 sulfur atom. There's another compound called iron pyrite, fool's gold, that is made up of iron and sulfur, but instead of having a 1-to-1 ratio, it has 2 sulfurs in it. Iron pyrites, fool's gold, is that beautiful golden color that looks so much like gold. Well, let's go look and see how we could make one or the other of these compounds. There's sulfur in there, and there's iron. And to prove to you that there is iron in there, I have brought a magnet, and perhaps you can see the magnet moving. Can you catch that? If not, let me dump that onto a piece of weighing paper. And I'm going to fold this weighing paper so I can transfer it back into this test tube. Now, let's just use a little bit of it, because I think you'll be able to see readily how the magnet makes porcupine quills out of the iron filings. The sulfur is still in there also, and so what we have here is a mixture. A mixture still contains iron atoms and sulfur atoms, and they are uncombined in a mixture in a 1-to-1 ratio. Let's go and see how to convert these into a compound, triolite. That's looking good. And we'll heat this up for a while until it turns red hot. And it'll take probably about 3 minutes for this to actually completely react. You see the sulfur fumes right now, and there's the glow of the reaction. I think we're done, except there is some sulfur left in here, and I would want to try to get that sulfur reacted with the iron in here. And so I probably should have used a little excess sulfur. Again, notice that some of the sulfur has not been reacted, but we do have this plug of Trilite that I'm going to get out of here and crunch into little pieces, make a powder out of it. It's fairly hard, as you might suspect an iron compound to be. Okay, now I need a piece of paper, and I'm going to put that on it, and let's see what it does. Here's the piece of weighing paper again. I'm going to put this sample down on here. And let's use this same magnet and see what happens. And you see there's not much in the way of motion going on with this sample. And so it has changed in that character. If I were to heat this up again, and let's go ahead and try that. And you see that it is heating up the test tube, but not much is happening in the way of reacting the iron sulfide. I'll stick this plug back in here so I don't get the sulfur fumes out here. But there's no reaction at all. So this substance is not reactive in the way that the mixture was reactive. And the reason for that, of course, is the reaction's already occurred. The iron's already combined with the sulfur. Let's go look at the board. What I did was I took 400 mole of iron and combined it with the same number of moles of sulfur. I heated it, and we got out iron sulfide. That temperature was on the order of probably 700 to 900 degrees Celsius. If we had taken iron, and instead of 1 mole of sulfur, we'd taken 2 moles of sulfur and heated it, I could have made iron pyrites. It would have taken about a month at 900 degrees and exclusion of oxygen to make the iron pyrite. But we don't have time to do that, and we've already seen that we can combine a 1-to-1 ratio. Here, this would have been a 1-to-2. The 1 is understood, and 2 is included to specify specifically that it would take 2 moles of sulfur for every 1 mole of iron, or 0.2 of a mole of sulfur for every 1/10 of a mole of iron. At this point, I'd like to consider doing something different. I'd like to talk to you about how this compound, iron and sulfur, are found biochemically. They're found biochemically in numerous compounds in living organisms called ferredoxins. They consist of a group of substances, Fe4S4, as a cubic arrangement, looking something like this, with iron here, and here, and here, and here, and sulfur here, and here, and here, and here. This is a very important biochemical substance. It's found in the mitochondria of cells that enable electrons to move and produce ATP, adenosine triphosphate, the energy-producing compound of living organisms. It's found in sulfur transfer agents. It's found in various enzymes. This group of iron and sulfur are in what are called iron-sulfur enzymes and compounds. Well, that's the limit of what I wanted to show you chemically. I think it's important now to show you some of the how we can deal with these masses and atomic weights with compounds. I have here some exercises I'm going to put on Blackboard for your use. Let's consider how to go about doing some of these problems.